Hello, welcome to our lesson on Sum and Difference Identities. So what we're going to do with this topic is add to our toolbox, right? We're going to add to the list of identities that we started to create in the previous topic. And some of those we had seen develop as we started creating the unit circle and talked about right triangle, trig. The identities that we're going to be looking at today are not so intuitive, and they are definitely not things we have seen before, unless you've been through a trig class before. But the proof of these and the where they're coming from is a little bit complicated to explain. I don't want to bog you down with that information here because ultimately we just have to be able to use these identities. But if you want to see where they come from and you think it would help in your understanding, just go on YouTube or go on Google and search up a proof for sum and difference identities, and I'm sure someone out there has done a wonderful job of showing where they come from. Okay, but for us, we just have to be able to use these things. So sum and difference identities are useful when we have the sign of a sum or the sign of a difference, and the same for cosine or tangent. If it's one of our sine, cosine, or tangent functions applied to a sum or difference of two things, what we can try to do is expand it out to further our abilities. For instance, we can use the unit circle. That was sloppy. Let me try that again. We can use the unit circle to find exact values for our trig functions at specific angles. Like if I wanted to know what is the sine of pi over 6, boom, right there on the unit circle, it's a half. Or if I wanted to know the cosine of 3 pi over 4, boom, it's right there. It's negative radical 2 over 2. Or if I wanted to know the tangent of pi, or the tangent of 180, I take my y divided by my x and I get 0, right? So there are all these angles that are on the unit circle that we can find the exact value for trig functions, right? Sine, cosine, tangent, secant, cosecant, cotangent. But what if we have an angle that isn't explicitly on the unit circle? For instance, what if I wanted to know the exact value for, instead of 60 degrees or 90 degrees, what if I wanted to know the exact value for 75 degrees? Now that's not explicitly on the unit circle, but these identities are going to help us with that. So the sum and difference identities are going to extend our ability to find exact values of angles that are not explicitly on the unit circle. Those angles are in there, they're just not labeled because they aren't as precise, and there isn't a pattern with them like there are with the other angles. And specifically what we'll be doing with these identities is using them to evaluate, so we're using them for evaluation purposes, verification as we saw in our previous topic, and simplification as we saw in our previous topic. Simplification. And some of these things kind of go hand in hand. The simplifying might help us to evaluate. Okay, so let's look at an example, and I'm going to be referencing the unit circle and these identities in the process. This is why I give you both of those pictures. But if I wanted to find something like the exact value for the sine of 75, up until this point, all we had for this, the only tool we had for this was, let's just put the sine of 75 in the calculator and make sure our calculator is in degrees, and it would tell us that the sine is about 0.966-ish. Okay, if I want the exact value, that's an approximation. If I want the exact value, I can now find it using one of our sine of a sum identities. One of our sum identities, it's the sine of a sum. So what I would do here is be a little creative. I would rewrite this as the sine of, instead of 75 degrees, I could split it up into 45 degrees plus 30 degrees, where I still have the sine of 75 degrees in there altogether, but because it's now the sine of a sum, I can use my identity to separate this out. So the identity says if I have the sine of a sum, then it's going to be equal to the sine of, I'm going to call this first one u, and then I'm going to call this one v. It doesn't really matter that you identify them that way, but just so I can follow along with the identity. So it's the sine of u, so the sine of 45, multiplied by the cosine of v, so multiplied by the cosine of 30. And then to that we're going to add the cosine of u, so the cosine of 45, and multiplied by the sine of v, so the sine of 30. Now that doesn't look much simpler, but sine and cosine of 45 and 30 degree angles, those are something we can get right from the unit circle. So using your unit circle, you would see that the sine of 45 degrees is exactly radical 2 over 2. And we would see that the cosine for 30 degrees is exactly radical 3 over 2. So the first part of this says we're going to multiply those. And then we're going to add the cosine of 45, which again is going to be a radical 2 over 2, multiplied by the sine of 30. And the sine of 30 is a half. So this is just algebra work from here. When we multiply the first two fractions, we end up with the radical 6 over 4. Remember, when we multiply fractions, it's straight across the top and straight across the bottom. And then when we multiply the second set here, we get a radical 2 over 4. Now we've already got common denominators, so we end up with a radical 6 plus a radical 2, all divided by a radical 4. That is the exact value for the sine of 75. And of course I could confirm with my calculator, right? The sine of 75, calculator says, is approximately 0.9659. If I put in my new fraction, I should get the same decimal. So I'm going to just verify rad 6 plus rad 2. If I divide by 4, I get the same decimal. Okay, so we were able to find an exact fractional value for that angle. Okay, now number 2 is basically going to walk you through the same process, but just so you can see it with the cosine identity. Again, we can rewrite this as the cosine of a sum, and just like the last one, I could say 75 is 45 and 30. Okay, so same process here, just a different identity. Now it's the cosine of a sum. And again, I'm going to call this one u, and I'm going to call this one v. So this one says our cosine of a sum says we're going to take the cosine of u, so cosine of 45, multiply it by the cosine of v, so the cosine of 30, and then we're going to subtract the sine of u multiplied by the sine of v. And then we're going to the unit circle to find each of these values. Cosine of 45 was radical 2 over 2. Cosine of 30 is radical 3 over 2. Those are going to be multiplied. And then sine of 45, radical 2 over 2. Sine of 30 is going to be a half. Those are going to be multiplied. So again, here it's going to be a radical 6 over 4, minus here it's going to be a radical 2 over 4. So our final result is, I can scooch this down a little, is radical 6 minus radical 2 over 4. That is the exact value for the cosine of 75. And again, let's just confirm. So if I change this to a cosine, and come on, cosine of 75, it's about 0.259, and then it should be a radical 6 minus a radical 2, and look at that, those decimal values are the same, so we've confirmed that we've done this correctly. Okay, so those two were pretty much the same thing, just using two different identities. Let me show you one that's a little different. Now, when the angles are in degrees, I think it's a little easier to conceptualize, like we can add, subtract, find differences and sums pretty easily. When the angles are not in degrees, when they're in radians, that's a little tougher. So rather than try to manipulate the angle in radians, let's just convert it. Okay, if we convert this, we know how to convert. If we had pi over 12 radians, multiplying by 180 over pi, we would convert it. 180 divided by 12 is going to end up being 15. So pi over 12 radians is the same as 15 degrees. So if we want to consider this 15 degrees instead of pi over 12 radians, then I think we can see a place to go from there. 15 degrees is the difference between lots of our angles, but I'm going to go with 45 and 30 again. I try to use the smallest angles possible. So I'm going to say that this is the same as the tangent of 45 degrees minus 30 degrees. And you can use any two angles you want that have a difference of 15. I just try to keep it smaller if I can. Okay, so tangent of 45 minus, or the tangent of a difference, right? This is the last identity that's on our list. The tangent of a difference, we can say is going to be equal to, and again, let me call this u and call this v. This is going to be equal to, on the top of the fraction, it's tangent of u minus tangent of v. So it's going to be tangent of 45 minus tangent of 30. And then on the bottom, it's going to be 1 plus the product of the tangent of u and tangent of v. Okay, so how does this look going forward? We'll go to the unit circle. At 45 degrees, our coordinates are radical 2 over 2 and radical 2 over 2. So when we go to find the tangent, remember that's sine over cosine. So if I divide the y by the x, I'm going to end up with 1. So tangent of 45 is going to be 1. And then the tangent of 30, so 30 degrees hits the unit circle at radical 3 over 2 and a half. So if I wanted the tangent here, I have to take 1/2 and divide it by radical 3 over 2, which means we're going to end up with 1 over radical 3. So tangent of 30 is 1 over rad 3. And that's going to be divided by 1 plus the product of the two values that we just found. So tangent of 45 was 1, and tangent of 30 was 1 over radical 3. So we have 1 minus 1 over radical 3 on the top of the fraction, and we have 1 plus 1 over radical 3 on the bottom. And that wouldn't be a terrible answer, but we generally don't want to leave complex fractions. We don't want to leave fractions within the fraction. So again, some algebra work here. I would simplify this. If we get a common denominator here, then all of the denominators are sort of irrelevant. We don't need them anymore. Or another way to clear out the fractions is just to multiply every term by the common denominator. So if I was to multiply every term in this fraction by a radical 3, our only denominator, then radical 3 times 1 is going to be radical 3, and then radical 3 times 1 over radical 3 is going to make those radical 3's cancel, so we're left with minus 1. And then when we multiply on the bottom here, we're going to get another radical 3, and then when we multiply here, it's going to be a plus 1. And so that is going to be our exact value for the tangent of pi over 12 radians. And again, let's use our calculator to verify. So let's go back to radians, and let's put in the tangent of pi over 12, gives us that decimal. And now let's put in our new fraction, which we're saying tangent of pi over 12 is going to equal that fraction. It's going to be radical 3 minus 1 over radical 3 and then a plus 1. And look at that, same two fractions. So those are actually equivalent. I'm on a roll. All right. Don't hold your breath. It's going to be a mistake coming. I can feel it. Okay, so next one is the same process, but we're working in reverse here. Notice how this one is already expanded out. So you're looking at a sine cosine minus a cosine sine, and if you look back in your table, you can see that that comes from the sign of a difference. Okay, so now we're going to actually put this back together. This is going to be our u, and then this one is going to be our v. Okay, so we can put this back together and say that this is the sign of a difference of u and v, so the difference of 80 and 20. And those are degrees. And that makes this pretty simple because 80 minus 20 we can subtract. This is going to be then the sine of 60 degrees. And then we can go straight to the unit circle to find the sine of 60. And the sine of 60 is exactly radical 3 over 2. If only they could all be that simple, huh? That was a nice one. Okay. How about this guy? Not a lot of space here, which I don't know about you, but when I'm looking at a problem and I see there isn't a lot of space, it's promising like, okay, it can't be that bad. So this one, the direction is to use a difference identity to verify. So unlike the others where we're trying to find exact values, we're going to actually verify. We already have that one side's equal to the other. So remember when we're verifying, we try to pick a side and simplify it down and transform it to looks like the other side. And we pick the side that's a little more complicated or looks more complicated. So we're going to go with this side over here. We have the sign of a difference. So let's call this U. Let's call this V. So the sign of our difference is going to be equal to just this side over here, right? Is going to be the sign of U, so pi over 2, multiplied by the cosine of V, so the cosine of x, and then we're going to subtract cosine of u, so cosine of pi over 2, multiplied by the sine of v, so the sine of x. And two of these things have values. So the sine of pi over 2, if we went to the unit circle, pi over 2, the coordinates are 0, 1, so the sine is just going to be 1. So the sine of pi over 2 happens to be 1. And cosine of x, can't do much with that because there's a variable in there, so that's going to stay as the cosine of x. And then we're subtracting the cosine of pi over 2. So remember, pi over 2 hits the unit circle at 0, 1. So the cosine is just going to be 0. So that's going to be 0 times the sine of x. Again, that's going to stay. It's got a variable. But what happens when we multiply something by 0? Well, then that piece is just going to go away. 0 times anything is 0. So once that's gone, we're left with precisely what we have on the other side. So this ends up being equal to cosine of x, which is exactly what we were trying to show. Okay? So not too terrible until we get to this last one. This is where we separate the weak from the strong here, people. No, I'm teasing, but this one is a little more involved. Now, hopefully you can see this is the sign of something minus something. Okay, so we're going to try to use our difference identity, our sign of a difference identity to try to simplify here. Actually, to try to evaluate, but in the process we are simplifying. So let's say that the cosine or inverse cosine of 3/5 is u, and let's say that the tangent, inverse tangent of 12/5 is going to be v. Okay, now that's a lot for us to wrap our brain around. Like, this expression looks really ugly. So let's try to unpack this a little bit. Okay, if the cosine, inverse cosine of 3/5 is equal to u, what does that mean? Well, it means that if we were to take the cosine of u, that we would get 3/5, right? That's precisely what our inverse function means. So the cosine of some angle being 3/5 means if we were looking at a right triangle, I'm going to use my little cheat tool here to draw myself a right triangle, and in this right triangle we had angle u. This means that the adjacent side would be 3 and the hypotenuse would be 5. And because we know the Pythagorean theorem, we could figure out the missing side, right? 3 squared plus some missing side, let's call it b squared, has to equal 5 squared. That's 25 minus 9 is going to leave me 16, which means our missing side has to be 4. That's a pretty common Pythagorean triple, so if you knew that was going to be a 4 without having to do Pythagorean theorem, good for you. If not, it's okay. Pythagorean theorem's not that hard. So that's just unpacked. We're going to hopefully see how that helps us in a few minutes, but let's unpack the other one. So in the other one for v, we said that the inverse tangent of 12/5 is going to equal v. Now what that means is that if we were to take the tangent of v, that it would have to equal 12/5, which means if we had a right triangle and it had an angle in it that we called v, then the opposite side would be 12 and the adjacent side would be 5. And again, we could use the Pythagorean theorem to find that missing side. So 5 squared and 12 squared would equal that missing side squared. So 25 and 144 is 169. If we square root that, our missing side is 13. And again, that's another pretty common Pythagorean triple. If you knew 5, 12, and 13 was going to be the missing number, awesome. Okay, so we unpacked that. Now, I don't know if that's helping you see anything happen yet, but it's coming, I promise. Okay, so we're saying that this is the sign of something minus something, right? So we're going to try to apply our sign of a difference identity, which says the sine of u times the sine of v, sorry, cosine of v. Oh, I knew it. All right, I was going to make a mistake somewhere. Luckily, I caught that one. Okay, sine of u times the cosine of v minus the cosine of u multiplied by the sine of v that's the identity itself, right? Now, that's what we're trying to apply here, but we don't have u and v. We have this mess that we've made on the other side, okay? So let's try to figure out what each of these pieces is. I need another color. I'm going to go ahead and go with black. The sine of u. Because we draw out this triangle, I think we can actually locate the sine of u. The sine of u. Here's u, right? If I wanted to take the sine, I need a fraction of the opposite side over the hypotenuse. So because I drew out that triangle, I know that the sine of u has to be 4/5. So that's going to be 4/5. The cosine of v. Let me use another color here. Cosine of v. I'm going to go over here to angle v. Okay, the cosine is a ratio of the adjacent side over the hypotenuse, which means cosine of v is going to be 5/13. So those two things get multiplied, and then minus the cosine of u. Cosine of u, we did that. That's up here. We already said cosine of u has to be 3/5. So that's going to be 3/5. And then lastly, I need another color. I need the sine of v. So the sine of v is a fraction, here's v, right? It's a fraction of the opposite side over the hypotenuse, so 12/13. So sine of v is 12/13. So because I was able to unpack what those inverse trig functions were, find missing sides using Pythagorean theorem, I have exact ratios to represent all of those things. And now it's just multiplying and subtracting. So this is going to become 20/65, multiplying straight across, and we're going to subtract 36/65, and 20 minus 36 is -16/65. So that is our exact value for that monstrosity that we started with. Okay, now let's go ahead and just verify. We've done all this work. Let's make sure it's right. So let's see. Can you handle this, Desmos? Sine of the inverse cosine of 3/5 is going to go in there. And then we're going to subtract the inverse tangent of 12/5. And we're going to close that off. Okay, so we get that decimal. And now let's put in our new fraction and make sure it's the same. Is -16/65 the same value? And look at that. We did it right. I survived this one unscathed. Okay, so there it is. This is a challenging process, but it's a process of rewriting. It's recognizing when you have the sine of a sum or the cosine of a difference or the tangent of a sum, or when one of those identities can be applied, and also being able to use the unit circle to find specific angles. And usually we can work within quadrant 1 and figure those things out. Alright, so you've got some practice to work on. Give it a shot, and as always, if you need some extra help, then reach out. Till next time, take care.